Welcome back, aviation enthusiasts. Today, we're diving into the fascinating world of flight dynamics straight from the official documents, which you can find the link in the description below. Buckle up as we explore the principles that keep us soaring above the clouds. In this video, we'll cover the essential forces and principles that govern flight. Whether you're a pilot, a student, or just curious about how planes fly, this is the video for you. Let's get started. First, let's talk about the basics. To control any aircraft, be it an airplane, helicopter, glider, or balloon, a pilot must understand the fundamental physical laws and forces acting on it. These forces include lift, weight, thrust, and drag. Lift is the upward force that counters the weight of the aircraft, allowing it to rise off the ground. Weight is the force of gravity pulling the aircraft down. Thrust is the forward force produced by the engine or propeller, and drag is the resistance the aircraft faces as it moves through the air. The atmosphere is a crucial player in aviation. Composed of 78% nitrogen, 21% oxygen, and 1% other gases, it has mass, weight, and an indefinite shape. Most of the atmosphere's oxygen is contained below 35,000 feet altitude, which is essential for both breathing and combustion in engines. Understanding the composition and behavior of the atmosphere helps pilots anticipate changes in aircraft performance. Let's understand why air is considered a fluid. Air flows and behaves similarly to liquids, displaying properties like viscosity, which is its resistance to flow. High-viscosity fluids like oil flow slowly, while low-viscosity fluids like air flow easily. This fluid property of air is essential for understanding how it interacts with the surfaces of an aircraft, particularly the wings. When air flows over a wing, friction causes air molecules to stick to the wing's surface, forming a boundary layer. This boundary layer is where the velocity of the air relative to the wing changes from zero to the free stream velocity of the air farther away from the wing. The characteristics of this layer are crucial in understanding drag. To measure altitude accurately, pilots use pressure altitude, which is the height above a standard datum plane where the pressure is 29.92 inches of mercury. Pilots adjust their altimeters to this setting to get a standard reference. Then there's density altitude, which corrects this for non-standard temperature. Density altitude is a critical concept because it reflects how the aircraft will perform in different atmospheric conditions. For example, high-density altitude, which can occur on hot days, means thinner air and reduced aircraft performance. As you climb higher, the pressure decreases, which directly impacts flight performance. This decrease in pressure affects how much lift an aircraft can generate and how engines perform. Humidity and temperature also play roles in flight. Warm, moist air is less dense than cold, dry air. This affects the density altitude, which in turn influences aircraft performance. High humidity and high temperature can significantly reduce an aircraft's performance by decreasing engine power, thrust, and lift. Pilots must understand these environmental factors to ensure safe and efficient flying. Now, let's get into the theories of lift. We have Newton's laws of motion and Bernoulli's principle of differential pressure. Newton's third law, every action has an equal and opposite reaction, explains how propellers and jet engines push the plane forward. Bernoulli's principle tells us that as the velocity of a fluid increases, its pressure decreases. This principle is illustrated by the air flowing over the curved top of the airplane wing, which speeds up and creates a lower pressure compared to the higher pressure on the flat bottom surface, generating lift. Airfoil design is where the magic happens. The shape of the wing, with a curved upper surface and a flatter lower surface, creates different pressures that generate lift. The camber of the airfoil, which is the curvature of the wing, plays a significant role in how much lift is generated. Modern aircraft use a variety of airfoil designs to optimize performance for speed, efficiency, and lift. For instance, high-speed jets may use thinner, more streamlined airfoils, while general aviation aircraft might use airfoils with a greater camber for better lift at lower speeds. Let's delve deeper into how lift is distributed across the wing. As air flows over the wing, there are regions of negative pressure on the upper surface and positive pressure on the lower surface. This pressure difference creates lift. The distribution of pressure varies with the angle of attack, which is the angle between the chord line of the wing and the oncoming airflow. As the angle of attack increases, the center of pressure moves forward, and lift increases until a critical angle is reached, after which lift decreases sharply due to flow separation and stall. Finally, all these principles come together in real-world aviation. From adjusting takeoff and landing techniques to understanding performance metrics, pilots use these concepts every day. For instance, knowing how pressure altitude and density altitude affect engine performance and lift can help pilots make critical decisions during flight planning and in-flight adjustments. So, the next time you see a plane soaring high, remember the science and engineering that makes it possible. Thanks for joining us on this journey through the principles of flight. If you found this video helpful, give it a thumbs up, subscribe to our channel, and hit the bell icon to stay updated with our latest content. Fly high and stay safe.